Hi everyone. Today I'm going to present the paper that is titled Exploring a Layer-Based Pre-implemented Flow for Mapping CNN on FPGA. So a little bit about me first. So I'm a fourth-year PhD student at the University of Florida in the Department of Electrical and Computer Engineering. I started my PhD at the University of Arkansas and I transferred in the summer of 2019 to the University of Florida. My research interests include machine learning, computer architecture, reconfigurable computing, and embedded systems. Here is the contact address for whoever has any additional questions after my presentation. Please feel free to reach out to me and I will be happy to answer any of your questions. So this is the outline that we're going to cover today. We're going to start first with an introduction and present some motivation for this work. Then we're going to talk about general architecture of CNN inference on FPGA. And then we're going to go deeply in the proposed design flow. We're going to then show some experimental results that have been performed on two convolutional neural network named LearnNet and VGG16. And we're going to conclude the presentation. The innovation in FPGA hardware architecture in the recent years provide the basis for unprecedented flexibility and acceleration in high-performance computing and embedded system application. However, it also requires car tools capable of extracting domain application-specific features to better leverage the resources in recent FPGAs. In Table 1, you can observe that the amount of resources available on Alveo 250 and Area 10 are reaching millions of logs. The off-shift memory, for example, of the Alveo 250, it's up to 64 gigabytes. Also, now regarding this amount of resources, FPGA architecture complexity now keeps increasing. So there is a rising need for improved productivity, performance in several computing domains, such as machine learning. The traditional design flow is the following. First, we set up first some specification. Usually this is done with the system description language. Then we move into the functional design. Here we use a hardware description language such as VHDL, Verilog, System Verilog. Then we do the logic synthesis tool and the circuit design, the physical design. This involves placement and routing. Finally, we download the bitstream on the chip. However, to perform physical implementation, Kyoto use heuristic. To generate the final design, they have to consider the number of cells into the design, their connections, the target FPGA physical architecture. They also have to take into account the user constraint. So the bigger the design, the bigger the heuristic algorithm have to work hard in order to reach the desired performance. However, car tools generally achieve better quality of result on small design as the resource application problem is smaller when compared to a bigger design. Those problems are known to be NP hard. So focusing on optimizing smaller modules may therefore lead to a better quality of result improvement in the design. As motivation example, we present four different applications that have been implemented in the 3x3 processing element with in both Vivado and the pre-implemented flow. We present here the compilation time and the maximum frequency achieved by each design. We're only going to focus here on the matrix multiplication operation and the smoothing, which is also known to be a convolution. The matrix multiplication also is usually used to implement a convolution. As you can see in both cases, the pre-implemented flow achieved better performance when compared to the traditional flow with Vivado. We achieve more than 33% higher frequency and 37% less compilation time. Now, regarding the CNN inference on FPGA, there are mainly two different types of architecture. the SIMD architecture and the stream-based architecture. The SIMD architecture usually works as follows. First, they fetch the feature maps and weights from external memory to on-chip buffers. The data are then streamed into computer engines composed of several PEs. The results are streamed back to an on-chip buffers, and if necessary, they are write back to the off-chip memory to be processed in subsequent CNN layers. Now, regarding the streaming-based accelerator, this type of accelerator usually tailor the hardware regarding the target network. The topology of such CNN accelerator is transformed into a specific layer-by-layer execution schedule following the structure of the data cyclic graph. The data cyclic graph is the topology used to represent a CNN graph. The intermediate result between the layers can be stored in registers, memory, or directly pipelined into the next layer. The main advantages of this type of accelerator is that it minimizes the latency caused by the off-chip memory communication and thereby reduce the power consumption. As we know, it's higher, the cost in terms of power consumption is higher when communicating with the off-chip memory rather than an on-chip buffer or register. It also helps the design to achieve a higher throughput. Now we're going to present the proposed design flow. It is composed of two major steps. The first one is called the function optimization. In the function optimization, we perform a design space where we want to implement the basic function of a CNN in order to achieve the best possible performance. To do that, we have to take into consideration some constraints such as timing, floor planning, and power. If the design space exploration results are satisfying, then the component are saved in form of the DCP or design checkpoint into a dataset. This step is semi-manual as the design architect must choose and precompile the component using vendor tools such as Vivado. But however, the advantages of this step is that this step is usually done once and the component can be reused for multiple CNN. The second step is called function architecture optimization. This step is fully automated and it aims to combine the pre-built component into a CNN architecture. The different functions that we can optimize with this design flow are the following: the convolution, the pooling layer. In the experiment that we're going to present, we only test the max pooling layer, but several pooling layers also can be implemented. So the number of components that can be pre-implemented can be also extended for different CNN architecture. But given the current version of the design flow, this is the function that the programming flow currently supports. So we have a convolution, pooling, rectify liner, and pooling connected layer. In this slide, we present a basic architecture of a convolution layer. So we assume that this is the input convolution that we receive. We have a 2D feature map with a certain number of channels. The input feature maps are processed according to the arrows presented in the picture. So the input are first load into shift register, which are considered to be on-chip memory on-chip buffer, and we have several on-chip buffer which works as and we in order to process data from those buffer, we use a ping pong protocol. So we first fetch the data into the first line buffer, the first on-chip buffer, and when the computation starts on this buffer, then the controller start loading the data into the subsequent buffer. All the data on the first on-chip buffer have been processed, then we switch to the next buffer and so on. So the data are then loaded into a computational unit along with weight and bias. The architecture of the computational unit is present in the picture of the right. It's a cascade of B that perform multiplication-wise operation followed by the other three. Once all the components have been implemented, now we're going to go through some performance exploration in order to produce DCP that can achieve maximum possible performance. The performance exploration step goes into several steps. The first one is called is in the first step we have to synthesize the component out of context. This allows us to implement an analysis and model independently of the rest of the from the rest of the design. It also allows us not to add buffer into I/O. Is another advantages of synthesizing the component out of context is that it enables us to reuse and preserve the characteristics of place and hard module within the top design. The second step is called floor planning. Here we use feedback constraints in order to carefully select the FPGA resource that each design component will use. It also helps us to improve the module level performance and area. By doing so, the designer can also use a minimum amount of resources instead of letting the car tool use as many chips die as it wants. It also preserves the quality of result of submodule in the final design. The third step is the clock routing. Here we just in this step we just perform a routing of each component that has been synthesized out of context. The fourth step is the lock logic. Once we go through the the three first step and we are satisfied with the desirable performance, we then can lock the placement and the routing to prevent vibrato for altering the design later when we're going to perform the architecture or composition. Then, after locking the design, we generate the checkpoint and we go through the component matching. The component matching step in the component matching step, what we do is that we recompose the final CNN architecture by stitching all the components together. As example, you can see the Linux CNN on the right. You can see how the components have been implemented. What are the interface between each component? We have an interface to on-chip buffer where the data will be streamed from one component to another. We also have a memory controller to synchronize the communication between each component. Once all the component has been also all the modern architecture has been composed, we have to place the final architecture. What we do is we recursively pass the input graph and place the first component. For each adjacent component, we assign a location on the FPGA grid. However, we want to be able to preserve the performance as much as possible. So we define then two cost functions, which is a timing and a conjunction cost, in order to assign to evaluate the cost of the assigned location. The timing cost help us to define the wire length between two components. But since each component has been pre-implemented individually, he has no idea of an existence of any other component. So when we stitch the components together, we create a wire length between those two components. So we have to carefully place each component in order to minimize the length of this wire between the two components. So we compute then the timing cost, which is the length of the wire between two components, and we also compute the conjunction cost. We also evaluate which is a weighted sum of the number of components overlapping in a tie. So the smaller the conjunction cost it is, the better it is. So once we are when we recursively pass the input card, we place the first component. Then before placing the second component, we compute the timing cost and the congestion cost. If those two values are smaller than the specified threshold, then we can place the second component and move to the next one. Once all the components are placed accordingly on the FPGA, now we got to do the internal routing, the internal component routing. So all the components have been placed and right during the first step, uh, but since wire have been created between them, we have to route those wires. The eighth step is, that's why the eighth step is needed. Now we're going to present some experimental result that has been done using our proposed design flow. So the evaluation platform, for the evaluation platform, we use a Xilinx Intel C plus FPGA. The components were implemented with Vivado HLS 2019.2 and RapidWire 2019.1. For benchmark, we use Lunet and VGG16. Here in those experiments, we want to measure the latency, the maximum frequency and productivity. Finally, the resource utilization. The first table presents the resource utilization of our two benchmarks. As you can observe in the first table, in most cases we use less resources than the baseline approach. It's only with DSP that the pre-implemented will use around 7 DSP more than the baseline approach. So overall, we can say that pre-implementing basic components have the potentiality of reduced resource utilization. So this is justified by the fact that Vivado can optimize individual components without some logic insertion while adding such resources when compiling a bigger design, which translates into also a higher power consumption. The second table presents the performance of each layer of the LUNET network and the overall frequency achieved by the pre-implemented design. So as you can see, for implementing each layer component individually have a higher achieve a high frequency. So the goal of the pre-implemented flow is also is we want as much as possible to preserve those performance when we're stitching the design back together. So one of the future work in our research is also to improve the overall cost function, timing and conjunction cost function in order to preserve those performance as much as possible. We also notice an improve into the latency and the maximum frequency. Now we're going to talk about the productivity when used the pre-implemented flow rather than the baseline approach. As you can see, for learner, they say productivity improvement of 69% and 61% for VGG when using the pre-implemented flow. The architecture composition with Rapid present only 5% of the total of the overall time. The biggest portion of the time is spent into the internal routing. This is simply justified by the fact that when the size of the design increases, the productivity is affected. This section shows how the proposed flow can leverage component reuse to reduce both compilation time and implementation cycles. Now we're going to present the performance of the VGG network. The first table presents all the components that how the VGG network has been pre-implemented by showing all the different components, the maximum frequency of each component and the latency achieved by each one. As you can see, there's an improvement on the overall maximum frequency, but there also is a slight increase into the latency. So when several design components must be spread around the chip, a rising issue is how to deal with fabric discontinuity such as erratic type pattern and I/O columns. This discontinuity increases the data path and have a negative effect on the performance. So in order to tackle that issue, the tool and set pipeline elements such as flip-flop on the critical path in order to improve the timing performance, but this has an side effect on the latency, which has increased the latency. So we come to the end of our presentation. As conclusion, we have proposed a pre-implemented flow based on the approach divide and conquer in order to accelerate model inference on FPGA. This flow takes as input an abstract representation of a CNN model inference to perform model mapping and design checkpoint generation by assembling pre-implemented CNN components with rapid write. Experiments and the results show improvement in terms of productivity, latency, and maximum productivity, with little to no impact on the number of resources used. We have reached the rest of the end of our presentation. If you have any questions, feel free to reach out to me. Thank you.